Okay, so the last thing that we're going to do is this is section 12.6, and it's on scatter plots, correlation, and regression lines. Okay? Scatter plots, we've actually talked a little bit about scatter plots before because it's just a way of graphing x and y data onto a little graph. And I apologize, the graph's small. I didn't realize my table was getting as big as it was before I did it. But what I've done is I've taken table 12.15 from your book, and you don't have to open this or anything, because it's the same exact table. Table 12.15 from the book, and what it is it is a model of people A through J. A lot of times when we do surveys, we try to anonymize the data so people don't get upset if they see their name they won't see their name in like a paper, especially when it says that they're like prejudiced against something or something like that. And then it tells how many years of education the person has, and then it also gives this score on some prejudice test that they were given. There's probably some pen and paper test where they were asked about their prejudices or how they thought about various people or blah, blah, blah. And they were ranked from 1 to 10. So all it is each person, the years of education, and the prejudice test score. A higher prejudice test score indicates that you're more prejudiced, okay, based on this test. So what we're going to do is we're just going to graph the data here using the x values here and the y values here. Okay, so I'm going to do that. So for person A, we've got years of education 12, and that's on the bottom, education. Years of education 12, and score prejudice test 1. So that's like right there, and that's person A. I'm going to write kind of small because my graph is a little tiny. B, 15 years of education, prejudice level of 7. 15, prejudice level of about 7, which is there, B. Okay, 14, prejudice level of 2. 14, prejudice level of 2, that's C. 13, prejudice level of 3. Oop, 13, prejudice level of 3. Should be about here. That's D. E, 8 years of education, prejudice level of 5. About here. E. F, 10 and 4. 10 and 4 is about here. That's F. G is 1 and 16. 16 and 1. Let's see, that would be here. And that is G. H is 11 and 2. It's here, H. And I is 12 and 3. 12 and up to 3 here. That's I. And finally, 10 and 4. Did we have a 10 and 4 already? We did. Oops, sorry. 4 years of education, 10 on the score. 4 and 10. There we go. OK, and that was J. Now, the question is, and it's a little tough to see because A, because the graph's a little small, and B, because the letters kind of get in the way of the dots. If you erase the letters, in fact, I'll do that. I'll erase the letters. It makes it a little easier sometimes to see what's going on here. So J and E and F, I and D and B, C, G, H, and A. OK. Now, what we've got is a set of data that hopefully tells us something about prejudice versus the level of education. Okay? Are the two quantities related? From this graph, can you tell if they're related or not? It's a little tough. One thing we can do is we can draw a little line called a regression line through this. And what you try to do with the regression lines, if you're trying to do it, you're trying to get an average. You take your ruler or whatever, and you try to angle it around so that it goes through the line you're going to draw basically goes through the most points. Okay, so if I'm going to do this, I'm going to try to get this pretty close here, kind of on an average, goes through most of the points. Let's try right about there. Whoops, that didn't go through most of the points. How about here maybe? Okay? And by through, I mean one side and the other, because you can't really go through. So I got about, maybe not quite right, but about half on one side, half on the other, about equal spread. If you're doing it with a calculator, you can get the regression line like perfectly, because we can figure all that out, although I'm not going to make you guys do that on here. But what you can do is now you can kind of see, is there a relationship based on that line between how much education you have and how prejudiced you are? Based on this data that we have, which is possibly made up for the book. Yeah, kind of. You can kind of see that as education level goes up, prejudice goes down. Does that mean that the more education that we can solve the prejudice problems in the United States by educating people more? Some people say yes, some people don't. Well, it depends what you mean by according to that. That's a good question. Some people are saying, no, you're crazy. Other people are saying, according to this data, yes. One thing about data like this, just because you can plot these things doesn't necessarily mean that the correlation, which is what this is saying there is a correlation between prejudice level and years of education. You can't say that years of education causes people to be less prejudiced. There could be lots of reasons why you're less prejudiced. It could just happen that because you happen to have more education, but you also happen to be around people who tend to be less prejudiced or something like that. Or you could be, it could be just a random, I mean, it could be just, not random, what's the word I'm looking for? Coincidence. Could just be coincidence or something. But you can use this in general to try to dig a little bit deeper into these things. Okay? So we use correlation just to see if there is some sort of a relationship between the two variables. In this case, years of education and prejudice. Let me give you another example of when correlation and causation are not linked together. Let's say the book uses an example of, let's see, what is the one in the book? It's about when the air temperature is greater, when it's hotter out, more people get stung by jellyfish. Does that mean that hot temperatures cause jellyfish to sting more? No. The jellyfish have no idea what temperature it is out. But what is also happening when the temperature goes up? More people are going in the water, right? When more people go in the water, that's where the jellyfish are. That's when they get stung more, right? So it's not really that the temperatures is what's causing that correlation between high temperatures and jellyfish stings. It's the fact that more people are going in the water, which might be caused by the fact that it's hotter out. I mean, there might be a doubly linked causation there. But the individual cause, you can't just say, well, now it's hotter out, oh, more people are going to get stung by jellyfish. Maybe you live in a place where you can't go in the water. In northern Australia, there's jellyfish all over the place. In fact, when people go in the water, they can get stung by these things called box jellyfish, which will kill you in like 15 minutes. Really, like, it's horrible, like scars if you don't die. And the funny thing about that is the way they prevent people who are swimming from getting, like lifeguards, from getting stung. They put nets out there, obviously, but they also wear, believe it or not, pantyhose. And you put pantyhose on your arms and legs. The jellyfish can't sting through the pantyhose, so actually it's fine. Now, you still don't want to go swimming out there, but if you have to be like a lifeguard and you want to save somebody, that's what you do. The other reason you can't go swimming up there is because of the crocodiles, which will eat you. So you can't actually go swimming in some places. So just because it's hot out doesn't mean more people are going to get stung by jellyfish there, strictly because you can't swim with the crocodiles, right? Okay, so if we do see a correlation, we'll get a line that makes some sense here. Okay, and I could have angled this line a little bit differently. But if you do the math and you actually plug it in and get the line, and the line goes up or down, then you can actually tell what the correlation is. Okay? Any questions on that? All right. Let me erase this one and show you what lines of regression actually look like in another form. So when you have a graph that looks like, let's say it looks like this, and you have a point here, and a point here, and a point down here or something, and the regression line goes through it like that, Okay? And normally you have more than 3 points of data, right? You really only need 2 to get a regression line, but that doesn't really make too much sense when you only have 2 points. If you want a good regression line, you want as many data points as you can. Okay? This regression line that I've drawn here, okay, this, if it's the best regression line, what it's doing is it's minimizing the distance between these points, okay? Between the points, rather, and the line. Okay? So if you take what you would do when you're trying to figure all this out is you'd average all the distances the points are from the main line. Okay? And you try to measure them vertically. I mean, you could go this way if you wanted to, but you try to measure them vertically in this sort of graph. Okay? We can designate how good a fit this line is by this thing called a correlation coefficient. A correlation coefficient. It's just a number, okay? And it's a number, it's generally given the letter R, probably for a regression line or something like that, okay? And it describes the direction and the strength of the relationship, okay? If you have a strong correlation, it's going to be a number close to 1. If you have a terrible correlation, it's going to be a number close to 0, okay? For my PhD, I had to do a whole bunch of data like this, and I was calculating these things all the time. So I'd write a little program to calculate all that stuff. But it's not that hard, really, once you figure it out. Okay? So this might not be a very good correlation, because there's kind of a far distance between those points, especially if it was like the data was all over the place like this. Yeah, that line might go through all the points on average, but it's a terrible coefficient of correlation. If all these points are in there, the coefficient of correlation might be like 0.3, which would be a terrible coefficient of correlation. Okay? If you had lines like, and actually that would have been a negative coefficient of correlation. I think it's negative because, yeah, it would be going from top to bottom. Okay? If you have a whole bunch of dots on a line like this, and your coefficient and your regression line goes right through it like that, this is going to be a really close. It's going to be like 0.99 or something like that, because it goes right through all those points. Okay, their coefficient of regression goes right through those points. If the coefficient of regression is like this is called a strong positive correlation. Strong because it's close to 1, and positive because the slope is positive. Okay? The other one we had before would have been a weak negative correlation, like that. Weak negative because the coefficient of correlation might be 0.3, negative 0.3. So it's negative because the slope is down, and it's weak because it's not close to 0. Or it's not close to either 1 or negative 1. Okay? Questions on that? Okay. This is going back to like the first day of class. Anybody remember what this was? A little final review. Absolute value. If the absolute value of R is near 1, that means you have a strong correlation. Okay? If the regression line is greater than 0, it's as one quantity grows. If one quantity grows, the other also grows. Okay? And if the coefficient of correlation is less than 0, it means as one quantity grows, the other shrinks. The other shrinks. Okay? Coefficient of correlation. All right. This doesn't tell the whole story, though. Okay? If you had 2 items in your sample, like there and there, well, what's the best line that goes through those 2? It's the line that goes right through both of them, right? Like directly through both of them. I'm going to move that one. There we go, OK? That is a correlation coefficient of 1 in that case. OK? But the problem is there's only 2 data points. So you can't tell anything really from those 2 data points. You can't tell a thing from those 2 data points. OK? This is why you want bigger samples. Bigger samples, smaller, you need a smaller R in order to indicate a correlation. OK? Does that make sense? The larger the sample size, the smaller the absolute value. No, it's the other way around. The larger the absolute value needs to be to get a good correlation. OK? All right. So let's see. On page 731 in your book, there is a big, long table. I'm not going to draw it out on the board. OK? It's a big table that says, let's see, this table is let's see, correlations in a population, the larger the sample size. So basically you've got sample size of 7. Hang on a sec. Sample size of 7. So hang on a sec. Hang on. I'm not sure what this table is actually telling us here. The larger the population, sample size is 7. OK. So this table here, there's a table in your book that gives what's called alpha. That's a Greek letter alpha. And it says 0.05. And what it does is it goes down and it says the sample population. And if you have a population of 4, 5, 6, 7, all the way down, then it gives an alpha value for each set of the sample size. So if you have a sample size of like 4 people that you look at, the alpha value tells you how close we are to having a good correlation. Okay? So in other words, an alpha of 0.05 says that we are within 5% of the correct correlation. Okay? So, and this also has another column, which is, there's a 0.05, and it's also got a column which is 0.01. Okay? And that tells you the smaller the value of R is needed for a correlation in the population. So for instance, for 4, it's 0.950, and for alpha of 0.01, it's 0.990. 0.990 and 0.950. For a sample of 7, okay, if you had a sample of 7, it's only 0.754 to be within 5%, and 0.875 to be within 1% of a correlation, what they deem as a correlation. Okay? To get which numbers? No, you can't quite do it that way. What you do is this is the value of R that you need. So for instance, again, so for a sample size of 7, let's say you took 7 people and you looked at 7 people, and you said, is there a correlation between something and something for that sample? If there's a correlation at all, to be within 5% of the, to be within, what is it here, 5% that's incorrect. In other words, 5% of the, let's see, the data in the population are correlated with a 5% chance that we are wrong. In other words, if we had a correlation value of 0.754 with 7 people in this sample, 7 different points, and it came out to be 0.8, we would say that we are within a 5% chance of being wrong that that is correlated. Does that make sense?
Yeah, but how do you get those?
These values they come up with using charts and tables and things. This is in a table. You'll look this up. It's in the table, right? It's in a table on page 5. I'm sorry, page 731. It says big 5 at the top. 731. Okay? So, question. The survey of 572 people. Okay? 572 randomly selected service members. Okay? Let me erase it over here. I'll put this down here. We're not going to have to do much calculating on this one. 572 random service members. Okay? It was determined that there was a negative 0.84 correlation coefficient for years deployed versus job satisfaction. In other words, according to this, you've got a negative correlation. As years deployed goes up, job satisfaction goes down. Okay? Now, the correlation for salary and job satisfaction, salary versus job satisfaction, was 0.75. Okay? So in this case, okay, this is the R value if you took salary versus job satisfaction. Okay? So which one is a better indication of job satisfaction? Years deployed versus job satisfaction or salary versus job satisfaction? I had heard about half and half. What do you guys? Salary versus job satisfaction gives you 0.75. Years deployed versus job satisfaction, absolute value is 0.84. Which one's closer to 1? Yeah, so it's actually this one is a better correlation. So if you want to know if the sailor or the military members are happy or not, you get a higher job satisfaction by looking at or you get a better measure of their job satisfaction by years deployed. If you want them to be happier with their jobs, don't deploy them as much. Basically mean paying them more doesn't help as much. Okay? What's that? Well, they won't make more. What's that?
So it's closer to 1 due to the absolute value.
Yeah. It's closer to 1 because the absolute value is 0.84 on this one, yeah. And the absolute value of this one's 0.75. So just because this one's, it's whichever one's closer to 1 when you take the absolute value. Yeah. Okay. So yeah, if you looked at this, you'd probably want to say, okay, we'd better look at how many years people deploy versus what we're paying them. But even though you get paid more when you're deployed, if you're in certain necks of the woods like we are, although it might be changing soon, I've heard. So we'll see. Hopefully not. Okay. So I am not going to make you calculate that. Although there is one more calculation you need to do. Grab your formula sheets. Okay. Actually, nope. I thought it was on there. It's not. There's no more calculations regarding regression lines. I was thinking they might have actually put it on there. If you want to look it up, I think it's in the book, and it's kind of an annoying long formula, but best for a calculator to be able, or a computer to do it. Yeah. Actually, let me at least write it on the board. I'm not going to make you do this. I just want you to see it. Oops. Okay. So here's the formula to figure out R. And now you know why it's not, you don't actually have to do it. If you want to figure out R, here's what you do. You take the number of samples that you have times the sum of each x and each y. You don't even have to write this down. Just observe. Hopefully I have room on the board to write it all. Sum of each xy minus the sum of all the x coordinates times the sum of all the y coordinates divided by the square root, and you can tell it's going to be long because I wrote that really, really long, of the number of data elements times the sum of all the x squared values minus the sum of all the x values squared. What this means is you add up all the x values, then you take the square. What this means is you do the squares of each individual value and then add them all up. Okay? Times, let's see, actually, it's going to be that times, times that, and then times another square root. You can't do it under the same square root. Times the square root of n times the sum of the y's squareds minus the sum of the y's squared. And that's what it is. So there's a reason I'm not making you do this, because it'd be a pain to do on just a regular calculator. It's just kind of annoying. You would do it in a table form again, where you'd have a table for each of these little parts, and then you'd add them all up, and kind of like taking the kind of like, what did we do the other day? Yeah, the standard deviation. It's a little bit like standard deviation. Okay? Once you have this, by the way, you can also figure out y equals mx plus b. In other words, the regression line itself. What you do is you find the slope, which is another one of these crazy formulas, but not too bad. Number of data points times the sum of the xy's minus the sum of the x's times the sum of the y's divided by n, sum of the x squared values minus the sum of the x values squared. Okay? So that's how you'd find the slope. We also have one to find the y-intercept, which is the sum of the y values minus the slope you just found times the sum of the x values divided by the number of points in your data. So I'll put this here. There. So it doesn't look like it's the same. And here. Those are your two formulas for figuring out that line, which is kind of cool. So you can easily program a computer to do this. Excel has it built in. If you're going to do graphs, you can actually just click on a little thing, and it says find regression line. And it'll draw the line for you through a bunch of data points. And then it will also give you the value of the slope and the intercept. It'll actually give you this line. And then it'll also tell you the coefficient here. So it's pretty cool how you do it. It's also not really that hard to actually program in there. Okay? All right. So we are done with new stuff. Woohoo! All right. Here's what I'd like to do for the rest of the class tonight. I gave you a whole bunch of handouts yesterday, I think 4 or so. The one thing that I didn't hand out that Will asked me about was the answers to the test for next week. I'll have to email those to you, or I'll put them on the website, but I'll email you a link to those so you can have the answer to those. But what I'd like you to work on, first work on this little sheet, which is just a couple things that we did here. It's, again, I'm not making you calculate any of this stuff. Actually, could you just hand that back to the... And then we've also got the one from last night, if you haven't finished that, the final exam test practice and the final test practice that's not the final exam. OK? Any questions so far on this stuff? All right.